Okay, does that look okay for everybody?
For me, it's perfect.
Okay, great. All right, well, good morning or good afternoon, depending on where you are. It's my pleasure to give this seminar to you today. So as Odd said, the title of my talk is From Maniacs to Micro-Force-Feeding Micro-Robots. Going to talk about some different families of micro-robots we've been making here in the lab for the past number of years for biomedical applications. So as many of you know, as you move down the length scale, you have the same physics apply, but the scale of the forces that are there change. And so if you are at the micro world, you have to deal with things like surface forces and friction, which can make things complicated. And so in the microrobotics realm, we're dealing with trying to manipulate and automate and use robotics to move around microscale objects, right? And so a lot of our work has kind of started in the traditional microrobotics area using a platform, a test bed, which you can see on the left here, which has a inverted optical microscope, which gives us a nice open workspace where we can put some micro manipulators or micro robots. In this case, we have 4 Cartesian micro manipulators, so 3 degrees of freedom, X, Y, and Z. They can move as small as 62 nanometers per step size. We have cameras, so we can do vision-based control. So whatever you can see from the microscope, you can get captured on the screen. And we're using point probes to do these manipulation tasks. And so we have designed some certain parts, about 200 microns or so in footprint with male and female features. And we can use these to examine different kinds of manipulation primitives and also assembly tasks. And so what you're seeing here is these series of micro manipulators actually using some learned models, which we used to figure out the best way to push the part from its initial position to its goal location. So we can plan a path around obstacles or other parts in the workspace. And then the system can automatically figure out, which manipulator to use when, where to push on the part in order to get it to its goal location. And so this is some of the traditional kind of microrobotics which we have seen over the years. And so now, if you go back here and instead of just using the microrobotic system to manipulate small scale parts, if the robots themselves are untethered and have wireless control, and are also on the same order of the micro scale, that's what we call a mobile microrobot. And so we've done a lot of work in mobile microrobots over there. That's really going to be the focus of this talk. And you can see here an example of some mobile microrobots that we've made. They're less than a millimeter in size. You can see them here on the US penny for scale. So why are we interested in looking at mobile microrobots? Well, they really give you unprecedented capabilities that you can't really get from conventional scale, larger scale systems. Our objectives, we want to make these wireless untethered robots sub-millimeter dimensions so they can get into these small spaces. And we want to be able to have them move in both wet and dry environments for different applications. Particularly for biomedical applications, you're going to have wet environments or sticky, complex surfaces, variable resistances. For manufacturing environments, you're typically going to have dry surfaces and you need very precise positioning and stable motions there. So how can we control these really small robots? So we use external fields, particularly magnetic fields. And so as the robot has some kind of magnetic properties, we can control it. So we can use a electromagnetic coil system and use gradients to control the robot. Or we can use a kind of a localized magnetic field system where we can have a specialized substrate. And we can use localized magnetic fields to also control the robot. So the robot can either be made of soft magnetic material. So this means that the magnetic properties are switched on in the presence of a magnetic field. So the polarity aligns with the major axis of the body. So if there's no magnetic field, it's not magnetic. But when there is a field, then it becomes magnetic. As an example on the left here with this I-beam shaped robot. And so the major axis of that robot aligns with the field lines as it moves around. This can just be simply sputtering nickel on some kind of photoresist. There's also hard magnetic robots. These are made out of permanent magnetic materials. So now in this case, the polarity is fixed. So it's always going to be in one direction at all times. These can simply just be permanent magnets, or they can be permanent magnetic particles embedded in some other kind of polymer. And so you can see some examples here of both of these types of robots. So one of our goals is, a futuristic goal that we have is to be able to make a mobile micro robot around the same size scale of a red blood cell, which has all onboard intelligence, processing, and manipulation capabilities. So we're a long way from that. So first we decided, okay, let's see if we can, come up with some micro robots which we can actually use for in vivo biomedical applications, and where we can, rather than having to fight the flood, the flow of the blood and blood vessels, where it's very challenging environments, can we look at applications in the GI tract, the colon, peritoneal cavity, where we can look at targeted drug delivery, diagnostics, and biopsy applications. And so all these regions are characterized by wet, sticky surfaces with complex geometry. So if you're going to be in the body, you want to control these magnetic microrobots, it doesn't really make sense to use a specialized substrate because you can't really put that in the body. So what you can look for is gradient fields. And so if you have a robot, say a little micro robot, and so you want to get this robot to move over to this cell to deliver a drug, and you try to pull it with a gradient, right? Since this environment is sticky and wet, it's really going to get stuck. It's going to have a lot of friction there. It's not really going to be able to get there. So what do? We have this rough terrain. How do we negotiate this rough terrain? So if you think about, what we do in real life, if we want to go a rough terrain with a vehicle, or we put really big tires on it, right? As we have these big monster truck vehicles, right, to go over this terrain, we put these really big tires and we roll over it. So we can take that same approach with our micro robots. And so here, instead of using a gradient field, we can now use a rotating magnetic field. And now we have the polarity of the robot will now follow the direction of this rotating field. So as this magnet rotates, the field rotates, the robot will rotate, it will tumble and do this locomotion to our goal location. Then once it's there, we can then release a drug or for this application. And so that's the idea behind these called microtums or microscale tunneling magnetic microrobots. So in this version of them, we make them out of SU8 photoresist with permanent magnetic particles, and we have them aligned in each of the ends of the dumbbell structure. And as we cure these particles and this photoresist, we can magnetize them in different directions. So we can have them magnetized so that with a rotating field, it will rotate in a lengthwise fashion or in a sideways fashion. And you can see the different kinds of ways we can align them as well here. And so these are small, it's about 400 microns by 800 microns in size. Okay, so here in this video, you can see a couple of different modes, the side view and top view of the sideways tumbling and the lengthwise tumbling. When designing these initially, we were looking at, which is the best geometries for the different ends of the robot. Is it best to have a rounded symmetric ends, asymmetric ends, maybe rounded corners, or it turns out the symmetric rounded ends are the best. We're able to control it to go vertical and horizontal directions. We can also modulate the direction of the rotating field so we can get certain trajectories. So here we're showing a P trajectory for Purdue. And also we can also have these robots go in various friction environments. So here we're showing we get locomotion in water and silicon oil and also on a dry surface. So there's very different friction properties there. And here, this view, you're going to show the robot jumping down this 90-degree cliff from the top and from the side. And so with this tumbling locomotion here, it's able to withstand that large jump. And then in here, we also did a number of tests to figure out what is the highest inclined plane that these robots can negotiate. These are both in dry surfaces and also in wet surfaces. So they can move up 45 degrees in dry environments. At 60, it gets a little tough. But in water, we can actually smooth over the friction coefficients a little bit in water and silicon oil, and the robot can actually move up these large inclines. And then finally, we have the robots here moving on different kinds of surfaces, a flat paper, knurled surface, cylindrical bumps, and also honeycomb terrain. So we get very good mobility with these tumbling micro robots. So once we're able to get that, said, okay, can we actually do some biomedical applications with these robots? So there's a couple of different things you need to, questions you need to answer in order to do this. So the first thing to use these in biomedical applications is first, is it safe, right? So are these robots biocompatible? All right, so we did some cytotoxicity tests with cells. We have a positive control and negative control, and we grew the cells on the SU8 material and also the material of SU8 with the particles. And essentially, green means that their cells are there. And so after at day 3, they're still alive, which means that the robots are non-cytotoxic. And we also made a version of these robots made out of PDMS and SU8 particles, and we got similar results as well. So pretty confident that these robots are biocompatible. And next, what we need to do is see if we want to be able to, deliver a drug for target drug delivery, can we load a drug onto the robot, and can we get the robot to release the drug? So we developed a electrospraying process where we could coat the robot with the mock drug payload and also some fluorescent coloring so we can actually see the drug. And then we put the robot into PBS buffer and observed how that mock drug payload was released over time by measuring the brightness of the fluorescence, right? So over about an hour, we're able to get, just through natural diffusion, 50% of the drug was able to be released. And as you move that up the timeline, you can also get 100% of the drug payload there. And so we can, depending on how much drug we need, we can scale the robot up or also increase the amount of electrospraying material and process that we have there. So the robots are biocompatible. We can get a drug on them, and we're able to get them to release. Okay, then the next thing we need to do, kind of the big part, is we need to be able to see the robot inside the body, and we need to be able to locomote in the body. And so we developed this test bed that you see here, which has a rotating permanent magnet, and we're using an imaging ultrasound system for imaging. And we all wanted to look at a couple different ways. So we looked at it in an agarose block, a gel block. If we put this robot in there, can we actually see it with the ultrasound system? So here you can see a nice image of the robot just doing this tumbling motion back and forth inside that agarose block. Next, we looked into a dissected mouse colon. So this is intact in the colon, and you can see a really nice view of the cross section of the colon and the robot moving up and down very nicely. That was dissected. Now we have an in situ intact mouse colon. So now the colon is still in the mouse. It's not alive. So we had to put in some Tylose solution to kind of prop open the colon, which is very a viscous fluid. So the robot, we're able to see the robot. It's able to move back and forth. It's a little bit slower than we'd like. So, but now actually with our in vivo mouse tests, actually works a lot better. We don't have to put that fluid in there to prop the colon open since the mouse is alive. And you can see we get nice smooth motion of the robot back and forth inside the live mouse. And so we started with mice since they're easy to use, a little bit easier accessible. But if you look at larger animal models, like a pig, we can see here the robots doing both the lengthwise and sideways tumbling inside a pig colon. So we have a lot more real estate here than you have in the mouse colon. And so you can see this is a little bit more closer to the human size. And so we're able to get some nice movement there. So what we're working on now is trying to optimize the designs of these robots a bit, looking at different materials and styles and different drug loadings to get therapeutic amounts of drugs, and also to get them to release on demand. So these robots themselves are fairly rigid. So inside the colon, that is fine, but there may be some applications in the body where the robots need to go over some delicate and soft tissues, like in the brain or in the spinal column. So in that case, you don't really want a rigid micro-robot. You want something that's softer. All right, so that's kind of the idea behind these MANIACs, which we call it magnetically aligned nanorods and alginate capsules. And so that's exactly what it sounds like. You have an alginate gel in a solution in a syringe, and where we have mixed them with nickel nanorods. And then as we push this solution with the nanorods out through the syringe, it goes through an aligning magnet. And this will align all these nanorods into one orientation. And then as it goes through the syringe, it goes through a high voltage system and a calcium solution to create these spherical capsules. And so then at the end, you can see what you have here. You get these magnetically aligned nanorods inside these spheres. So then now that these are aligned, they're in the spheres, we can then use a rotating magnetic field to have them roll. We can also, since they're porous, we can also soak in a dye or a drug into the robot, and then we can also use natural diffusion to release the drug. So here we're looking at kind of some inclined plane tests to see how well the robots are negotiating some of these harder terrains. And obviously, as the faster you turn, 2 hertz to 5 hertz, the speed is going to go up, and the higher the incline, the slower it's going to go. So that's kind of what we expected, and so it's able to go up almost 50 degrees, 55 degrees to 65 degrees, depending on the velocity. So inside the spinal column, there's going to be cerebral spinal fluid, which the robot needs to be able to locomote against. And so we're testing some modest flow rates here with the robot to see if it could actually withstand that flow and locomote against it. And so we can see it with both with PBS fluid and then also with diluted blood flow liquid to see how well it does. And so we're able to get motion against the flow. You can see when the field is turned off, the robot will kind of move back with the flow, but against the flow, it's able to negotiate that. So here's an example of a mouse brain. So here we're trying to deliver some doses of this drug at various locations, which we have prescribed ahead of time. And so what we do when we have the loaded dye in the MANIAC, we can go to our goal location. We can just rest there for a certain amount of time, and then you can see that the drug will then diffuse out of the robot at that goal location. We can also do this on a spinal column. Here is a mouse spinal cord, and so we are showing that the robot can move up and down the spinal column and also deliver these types of drugs there. Okay, so showing two examples here for these microrobots for in vivo applications, but there are also in vitro applications for these mobile microrobots. And so a couple of things are common about these applications. So first, you may want to use these microrobots to do safe micromanipulation of single cells. In order to do that, you need to be able to control the amount of force you're applying to the cells so you don't damage them. Another application would be to for tissue engineering, you may want these cells into desired arrangements or locations. So again, you want to make sure that you do that safely so you don't apply too much forces there. And then for cell characterization, tissue characterization studies, you're going to want to apply known forces to the cells at certain locations so you can study what's happening there. So for all these cases, if you had a mobile microrobot with an onboard micro force sensing, it would be very useful. And so that's the idea behind our micro force sensing mobile microrobot. So that's what you see here. So we designed this to have, we have a silicon frame on the outside of this robot, along with a compliant spring, and then an end effector. And on the back end, we have a small magnet. So with this small magnet, we can use magnetic coils and gradient fields to control the position and orientation of the robot. And then as it pushes on a cell or tissue, this spring is going to deform. And we can calibrate this ahead of time. So it's a very low stiffness spring. So as it's pushing on this, it's deforming. We can track the deformation with our microscope or camera vision system. And if we know the stiffness and we can observe the displacement in real time, we can back out what the force is. And since these are very low stiffness devices, these are on the order of micronewton levels. So how we make this, there's a series of steps here. Essentially, we need to first make a mold in the silicon wafer where we can define our spring. So we do some patterning and etching in order to make the pockets for the spring. And then we'll pour PDMS into that mold. We will cure it. And then once we have that cured, then we can do some more photolithography and etching to define the outside of the robot frame. And then we do a backside etch to release it. And then once we have the structure here, then we can physically, we'll add a magnet to the back of the robot. So these are some examples of this robot in action. So here, when it's showing up on the left, we're tracking the position of the end effector relative to the main body. And we want that relative displacement in the X and Y direction. And we can coordinate that with just in the X and Y direction of the spring and calculate the force. So we're showing the force in the bottom of the screen here in yellow and also in the bottom of the screen here. On the right here, we're actually telling the robot to autonomously go ahead this location and apply a force of 6 micronewtons. And once it applies a force of 6 micronewtons in the Y direction, it will then automatically back it off. And so you can see that as the forces go up on the screen, once it hits that target value, it will back off there. And then another example, the different end effector on the lower left is for manipulation. Here is trying to manipulate these little parts into a particular location, all while monitoring how much force you're applying to make sure that we're not going to damage the cells. And similar application here on the bottom. So this works very well. One of the issues is the PDMS spring is clear, transparent, so it's really kind of hard to see exactly what's going on at all times, and you want to be able to track it a little bit faster. So here we're around 5 hertz or so. We did some processing on the GPU to get up to 12 hertz, but still we'd like to get a little bit better performance than that. So one way we can help track these is if we use colors. All right, so we designed a new version using color tracking fiducials. So now, not only do we have a PDMS spring, we also have some colored PDMS marks inside the robot, which we can track. And so now you can track these very easily and faster. We can get a little bit faster throughput. So this fabrication process is very similar, except now we need to make 3 different molds for the 3 different colors of the PDMS. We have 1 color for the spring and then 1 color for each of the other markers. So once we fabricate the spring, and then marker 1, marker 2, then we can go ahead and do our similar process to define the back frame of the robot and then etch it out and add our magnet to it. Okay, so from before, we were able to get up to about 12 hertz using this surf-based tracking algorithm. Now, with the colors, we can just make a color mask, and we can track the spring, we can track 0.2, 0.3 very easily, and get the 20 hertz without even doing any GPU speed up. And so we can also, with the way we make with the PDMS, we have different ratios of the base material to the curing material. And so we can mix that in different ways to kind of tune the stiffness. And so we can tune the stiffness so we can get a resolution anywhere from 0 to 100 micronewtons with a sensing range of 0 to 100 micronewtons and a sub-micronewton resolution. It also depends on the accuracy of your tracking algorithm and your objective. So we can kind of tune it to wherever we need to. And so you can see examples of different kind of robots and their different stiffness properties here. So here we're doing a teleoperated test here. We're having the user first go ahead and do 3 control pushes on this substrate and then having them move this part. And we have a threshold of about 20 micronewtons. We don't want the user to go over. In this case, we're not giving them any feedback on how much force they're applying. So as they're pushing the part, they routinely get way over this desired threshold. Now we're giving them force feedback information on the screen. And so when we are below the desired threshold, the text is green. And when it goes over it, it turns red. And so you can very clearly see the different colors very nicely on the robot. After we do these 3 test pushes, as the users now manipulating this part, they're able to see if they're getting over that threshold. And if they are, they can kind of back it off. And so if you look at our plot here, we're able to keep these forces right around the desired threshold that we want. And so it's able to now, very easily, keep the forces in a safe level to do these control manipulation forces. Okay, so we were able to add colors to these robots to help identify them and tracking using this, multiple steps of this molding different color PDMS. But that's not the only way that you can get colors on a robot. And so our next project I want to highlight is using something called structural color. And so here we're trying to develop a 3D printed helical swimming robot, and we want to be able to identify each of these robots by by having different colors on the heads of the robots. And we're going to do this using 2-photon lithography or 3D printing. So what exactly is structural color? All right, so structural color, this is the same way that butterflies or beetles give off color. It's not with different pigments. It's actually by different micro nanoscale structures which absorb and trap light in different ways. So if you look at a butterfly and you zoom in, you can see all these different kind of nanoscale features, and same thing with some of these gemstones. And so some folks have looked at structural color using photolithography techniques, which you can see here. We wanted to see if we can actually get a similar effect just using 3D printing. And so this is kind of the process. So we put some photoresist on our cover slip. We will then do our 2-photon lithography to define the structure of our robot. We'll coat it with then some nickel and germanium, and then we'll put it in some water and we'll release it. And then we define these different patterns onto the head of the robot. And depending on how we will then project the light at different incidence angles, we can get different colors to be expressed naturally just from that structured pattern. And so we looked at various types of patterns, varying the length, the width, and the height of these structures, and also the spacing. And you can see here all the different colors that we can get depending on the angle of the light. So you can see here, these were from the different types of block dimensions. Here, you can see all the different kinds of expressions that we can get. We can also get out of plane color expressions, so we can use this to kind of check out the pitch of the robot as well. Depending on how it's pitched, we can get different expressions as well. And so we can use these now to track the robot. And so here we have it both at low frequencies and high frequencies, different rotations. We also can look at it. They show a little bit better on the white background and on the dark background sometimes. Then we can just use a simple color mask now also to just track the head of that robot as it moves around in the workspace. So that's kind of a neat way to kind of get color on these small scale micro robots. So if you notice, these tails on these helical swing robots, they're printed and they're rigid tails. All right, so they're going to be optimized performance for one particular environment. If you actually want these robots to be in the body, swimming through body fluids, these body fluids can be very different in different patients, and also depending on what kind of diseases they have, even along the different tracks that you're going. So really, you want to be able to kind of adapt the tail of that robot depending on what the environment is in. And so we started looking at how we could do this. So rather than using rigid materials, we want to see if we could, make some tails out of some tunable materials where we can change its properties. And so we started looking at hydrogel based micro robots, so we could get this advanced kind of adaptive locomotion capabilities. So we started with just modeling to see if we could come up with an idea of how these behaviors can change. So we looked at just a straight rod of hydrogel material, a bilayer with different cross sections, and we looked at how they change with different temperatures, so increasing the temperature and decreasing the temperature, and seeing what different kinds of states we could get. So if the structure is in its contacted state, even if it has a rotating field, it's not going to move. So it's how we can get independent behavior if we have two of these in the workspace at the same time. We also can go up or down or change the geometry as well. If we want to go through a smaller constricted area, we can shrink it down and change its properties depending on the environment. And so we also noticed that you can't get a regular state, a rod state, or contacted state all depending on the geometry and initial conditions. Some configurations give you all three states, but not all conditions give you all different states. So with this information, it's like, okay, we kind of have an idea now that we can adapt these and how they're going to change. Can we actually use this and to design a robot? And so that's what we started with an idea for our hammer micro robot, or helical adaptive multi-material micro robot. So here we have a hard magnetic head with the robot with an adaptive hydrogel tail. Okay, so what we wanted to do, we wanted to look at the hydrogel tail and see if we could understand how we can control this deformation as it changes in different environments. So we set the geometry of the length and the width to be 20 microns wide, 400 microns long. We set the width of the soft and hard regions, also both 4 microns. So we have this hydrogel material. Using 3D printing, we can adjust the laser powers as we print it. And so if we have a higher laser power, it will be polymerized more, be a stiffer material. If we have a lower laser power, it'll be a soft material. And so we can use those difference in stiffnesses in order to get this kind of curling behavior in different environments. And so we set most of the geometry the same, and we wanted to examine the differences, this modulation angle theta, as we changed it from 0 to 90 degrees. So you see the examples here of the tail as printed, and then what happens if it's in an IPA material versus DI water. So you have a tighter number of turns and configuration here, and a looser configuration in IPA. So here, if you're seeing the difference in theta, so theta from 0 to 90 on the right, in both of the two different solutions, IPA, isopropyl alcohol, and then DI water. And so you can see how the geometry changes based on that modulation angle. Then we can characterize the helix based on its geometry of its pitch value, its diameter, helical angle alpha, and then how many turns it has. And so we can see how these different behaviors you get in the different solutions corresponding to the different modulation angles here. So we decided to make a couple of robots with these. And so what we do now, we need to make a magnetic part of the robot. We want to be able to use a rotating magnetic field to get this to rotate, and then the helix will then propel it through the liquid. So we started off with an SU8 adhesive layer, and then we added some SU8 with permanent magnetic particles in it. And once those particles, and then we actually added another cover layer here onto the robot itself. And then we have to align these particles. So we put it into a machine. We pulse it with a large magnetic field in order to align all those particles in one direction. And then we bring it into our 2-photon lithography system, where we can now 3D print this connector, a hydrogel connector here, and then a tail. So once we have this connector, then we can print the tail, and we have 3 types of tails that we print. One is where it's totally aligned actually with the head. One is at a minus 45 degree angle here. The other one is at a minus 45 degree angle, but our modulation angle is kind of up to the left as opposed to up to the right. The reason we do this is because of some of the pre-stresses in the tail that are there will cause it to deform in different ways once it's released. And our ideal structure is when this tail is actually aligned exactly with the head. And so the one that does that the best is actually the type 2. So the type 1 ends up with the tail kind of going up. Type 2 ends up with it being aligned, and then type 3 ends up with the tail going down. And so this is what we can get. This is in DI water, and this is in IPA. And we wanted to investigate the type 2 because they have the tail aligned with the head. And we looked at 22.5 degrees and 45 degrees for the modulation angle. And so you can see here how the robot will move forward. At the lower frequencies, it kind of wobbles a little bit. But at higher frequencies, it actually has a straighter propulsion and a faster speed. And so if you look at the frequencies versus velocities for the theta equals 45 degrees, you can see that we do get a step out frequency here. But at the 22.5 degrees one, we don't get a step out frequency. So as long as the frequency is going up, the robot velocity is continually going up. So which is nice. And also we can also see that it can move very fast. So if we quote some of the literature that's there, these robots can go almost 10 body lengths per second, which is the fastest one for these 4D printed swimming micro robots that's there. And that's mainly due to the magnetic properties of that permanent magnetic material in the head that's able to keep up with that field and also that modulation angle. So here we can see some examples of the tail going from DI water to IPA. So here we're removing the water. And then we're going to add the IPA into the mix. Now we're adding IPA. Now you can see the deformation of the tail into a second different configuration there. So in this case, these heads are fixed to the substrate so they don't wash away. Now we're going from, now it's an IPA. So we're going to remove the IPA. And then we're going to put in the water, and you'll be able to see the change in the tail here as well. Okay, so now you can see how it's more coiled, tighter configuration. And so how do these guys actually swim? So now this is at 200 hertz. Okay, so it's a little hard to see. There's one here and there's one here. All right. So the one in DI water goes a lot faster since it's a lot less viscous material than the IPA. But now if we actually go to the 22.5 degree case, right? So we have the IPA in the top, DI water in the bottom. We'll see that the one in the IPA actually goes faster now, even though it is in the more viscous fluid. That's because we can adapt the geometry of that tail to fit that environment. So this shows that we can do this adaptive locomotion and get these advanced functions for these micro robots. So in the future, we're working on right now is can we actually Can we actually print a functional end effector to end these robots and use them for manipulation tasks? We also can functionalize them for drug payloads as well, for targeted drug delivery. And so those are some of the things that we're working on in the future. And so in this case, we're trying to get these advanced functionalities by using these responsive materials along with these magnetic properties of the robot. We also can get some more functionalities or multi-modes of operation, kind of playing with the different magnetic properties of the robot. So if we take a permanent magnet, right, the permanent magnet always has some fixed polarity and orientation of its magnetic field. And then if we can control the direction of the magnetic field and the gradient of the magnetic field independently, right, we can get something where we can have kind of translation with a fixed orientation, right? So in this case, so we have a permanent magnet inside this housing. It has a fixed orientation, so we can keep the magnetic field constant, and we can vary the gradient. And so we'll get the robot now to move with a constant orientation, right? And so that's kind of what we're showing here. So we have this translation with a fixed orientation, right? It can move side to side, it can move up and down. And so this is just kind of moving things around with a magnetic gradient. So now, to get some advanced functions, what we can do is we can now decouple this. We can now control the direction of the field along with the magnetic gradient, and we can now get it to follow that, so we can always have it going in a certain direction that we want. All right. So in this case, all right, so we can say we want to say push with this side of the robot. So it's an end effector of a certain kind, right? It'll move it along the orientation, along the gradient, and we want to direct the field so that it's going to move in this direction. In this case, if we want to move, say, with this end effector here in this direction, we also need to control the magnetic field orientation so that it's always going to move in that direction. So that's what this looks like here. So here we're moving head first here with that pointer end effector. We're rotating the field direction as it moves, kind of doing like a kind of a square path pattern here. So we can play with controlling the field direction and the gradients themselves, right? Since we're also able to control so the direction, the gradient, we also can use rotating fields as well. So if we use a rotating field with the same robot, we can also get a tumbling motion, right? So now you can rotate this field with a clockwise rotating field. It will move now this direction. If we do a counterclockwise, it will tumble this direction. So we can get multi-modes for this robot just by playing with the magnetic properties of the field, the magnet, and the magnitude and of the robot itself. And so what we did here, so we printed, again, we used a 3D printer, we printed the structure, and we placed in a very small 250 micron cubic magnet inside the middle, and we designed different end effectors. So this is designed kind of a splitting end effector if we wanted to kind of push these cells or objects apart. This is a catching end effector. We can actually catch a cell or a particle on here. It has a very big pocket. If we just want to push something, we have a smaller, shallower pocket here, and we can use that to push things around. And so here we're showing how we can capture a cell or an object and go up an inclined plane using our tumbling locomotion. Then here we're showing we're using the pushing end effector here to assemble these little spheres in a small spherical pattern there. Okay. So showing a couple of different families of mobile microrobots here today. We've shown the microtums, which is the microrobots for in vivo targeted drug delivery and diagnostics in the GI tract right now. We talked about the MANIACs. These are designed for in vivo targeted drug delivery tasks in the central nervous system, like the spinal cord or the brain. Talked about the microforce sensing mobile microrobots, which are primarily for in vitro biomedical applications like single cell manipulations and tissue characterization studies and tissue engineering applications. And we talked about the hammers. These are the hydrogel-based shape-changing microrobots for adaptive locomotion. So these will eventually be for in vivo biomedical applications. And then finally, we have these dual locomotion mode multifunctional magnetic microrobots for advanced functions. These typically could either be in vitro or in vivo biomedical applications just by playing with the different types of magnetic moments and controls that you have with these robots. So I just like to acknowledge all the students and postdocs who worked in these various projects and my collaborators as well, and the funding sources. And I'd be happy to answer any questions that you guys have on any of this. Thanks.
Thank you very much, Dave. So don't hesitate in the audience if you want to ask questions to use the chat so that we can read your questions. So I have one comment from the beginning of your talk. Conti is telling you, hello, Dave.
Oh, hey, Conti.
Well, I had questions, in fact, because you are showing very nice videos with the microrobots, but we know that generating the magnetic fields is also a big issue. So could you tell us a bit more about your magnetic actuation systems? And do you have only one? Do you have a lot? One for each experiment?
Yes, good question. We have a couple custom-made systems and one commercial system. So we have our own kind of 4-coil electromagnetic system, which we can use for gradients, gradient-based control. We have a rotating magnetic field system where we have a kind of permanent magnet, which I showed, the microtumblers, which rotates, and then there's also a servo motor on the bottom, which can control the orientation of it. We also have a Magnobotics magnetic field generation system, a commercial system, which really helps for our calibration studies, since we can control certain magnitudes of gradient and magnetic field directions and rotating and high frequency fields as well. So that can go up to 200 hertz, which we use, but at some point the field strength drops when it gets to the high frequencies there. So we have a couple of different ones depending on what experiments that we're doing.
And what's
but yeah, that's those are very useful.
Sorry, what's the typical workspace that you can reach with all these magnetic actuation system?
I would say probably a square inch right now. Now, depending, we could probably go a little bit bigger if you have bigger coils or bigger permanent magnets. But right now, since we're working mostly with mice or rats, that's kind of our workspace, which works well for us. If we go up, we scale up, we're going to need bigger magnets. And then we'd probably need to also move the camera or the ultrasound system with it, right, for larger workspaces. That's something kind of working on in the future.
Nice. So now we have a comment from Cedric. Hi, Dave. Great and inspiring talk based on very recent results. Thanks a lot.
Sure.
And a question from Conti. Thank you for this very nice presentation. Which sensor do you think better for sensing microrobot pose, 6DoF, in the human body?
Oh, that's a challenge, right?
Yeah.
Yeah. Yeah, so I know some folks are working on, trying to solve the localization issue inside the body, right? So people are working on doing this with magnetic, Hall sensors, things like that, to try to understand where the magnets are. That's mostly for position. Getting pose inside the body is going to be difficult. So with the ultrasound system, for our tumbling ones, we can see it pretty easily where it is. Those are all, those can also be fairly large, almost 600, 800 microns or so. If you're going smaller than that, I'm not sure what the limit is with the ultrasound system of what you can see. It may just be a white speck. I don't know. I guess it kind of depends on what your application is, if you need to get a focused imaging system there. With MRI, I think if you have magnetic material, it's going to have a lot of artifacts, so it will be very bright. So I don't know. There's probably, I'm sure there's some folks working on that. I'm not sure what the limit is. How are you going to get that pose information? I guess it depends on how accurate you need it. You can always approximate it with some of the imaging techniques that are there right now.
Nice. You have questions from Cedric. He has several questions. First, the relative stiffness of the robot versus the stiffness of the object is always a key question. What is your opinion on this key point? Do you think we must try to have a robot force sensor with a stiffness 1 order of magnitude higher than the one of the object to make it work well? Yeah,
that's a great question and a great point. I think so, because if the object you're trying to push is a lot stiffer than your robot, then the robot's going to deform, and then you're not going to see any action in the object, right? That's not going to deform at all. So I think there needs to be a difference there, and the nice thing about the force sensing robots that we've designed, we can tune it. You can tune the ratios when you make the PDMS to make it stiffer or lower stiffness or higher stiffness. And it's also a function of the vision system too. So the more accurate you can track that, the more sensitive you can make those measurements too. So I think it's going to have to be application dependent, and you're going to want to have to choose that difference accordingly. So you may not know ahead of time. So you may have to try one and see if it doesn't work. Then you try and go up or go down for another one. But at least these are you can make them in batch, and so they're kind of cheap to make. So hopefully you'll have a couple that you can choose from.
So I had a question on your micro FSMM robot.
Yes.
If you can go to the slide, it was on the video on the left.
Okay, hold on, let me go back. Oops, hold on. Okay. Which slide?
I don't know. You have a video, yeah, maybe this one, because it was about a video. I was wondering if it was automatic control or not.
Yeah, so this one on the one on the right, the one on the right is autonomous.
Okay.
Yeah, so we gave it some waypoints. So it has a starting location, it has a goal location here, and so it's trying to go to the left. Then once it's kind of lined up with that position, then it'll change its orientation and it will track up and try to track that position. And so this is actually slowed down quite a bit. This is half speed because it kind of happened very fast. And so since if we were doing it manually, it would be hard to do that. So having this with a closed loop, it makes it possible. So that's what.
So it's position control. Do you have force control as well, or?
Yes, yeah. So what it's doing is controlling the position, and then it's monitoring the force. Okay. Right. So once the force gets to that goal location, goal amount, you can see it here. Yeah. Then it'll back off.
Okay, thanks. And the one on the left, I'm just curiosity. Yeah. Bottom left.
So the ones on the left, these are manually controlled, but the force is in real time, right? Showing it in real time here. Yeah.
Another question from Cedric. Do you think that traceability of the force in the specific field of biomedical application is of key importance?
Yes. I mean, I guess you want to know that you're not going to damage the cells, right? If you're moving them around. And so you want to be able to report if you know what the force is, you can say, okay, all the forces were below this threshold, which can damage the cells, so that would be good. If you're trying to do like mechanobiology studies, especially so, then you definitely need to know what force is, because you want to be able to understand what the mechanotransduction mechanisms are. So you want to know what force you apply, when you apply it, where you apply it, and then how that affects the behavior of the cells afterwards. So that will be big.
So Kanti, thank you for the presentation. And you have one more question from Franco Pinan Basfaldo. Very nice presentation and impressive results. One question, are the structures printed around the permanent magnet, or are the magnets attached later? And in that case, how do you assemble them?
Yeah, great question. So they're attached later, and the way we do it is with a very skilled graduate student who uses tweezers. So that's a tedious process. But we actually made some fixtures for that now to help with that process. So you kind of have a magnet on the bottom, and so that will then help you align the magnet that you want to put on there, and you can put it in. And you can use glue. Sometimes you can use unexposed photoresist, which hasn't been cured inside there, and that will actually glue it in itself. You put it with a little UV light. We need to be very dexterous about it. So right now we have a new fixture we're designing and using it with our micro manipulator. Hopefully we can get it more automated and a higher throughput. But really, it's a practice with a grad student is what
I'm pretty sure he's having, I'm pretty sure he's having the same issue there of assembling.
Yes. Yeah. And so the reason we went with that case is, tried to print with particles, and it's really hard to 3D print with the particles. And so we use a nanoscribe system, just because you need a certain density of particles to get an effect that you want. But the higher concentration, it messes up kind of the laser where it's going to polymerize. So it's kind of a fine, sweet spot there, which is hard to get. So we haven't been able to figure that out. So it's okay, what else can we do? And so we tried to, let's make the structure, and then we'll put the magnet in ourselves. And then we're able to get some custom magnets made a small size. So we were able to kind of get them in there for our robots.
So comment from Cedric. Cool. Thanks a lot. Very clear.
Sure.
And I have one last question, if I can.
Sure.
From the last video you showed, so you have magnetic robots with tips pushing apart. It really looks like the very first video that you showed with the tips attached to the manipulator. Are you planning to use previous work and previous control laws and control strategies on these new microrobots?
Yeah, we would love to. So we were just kind of, right now, we're just kind of proving functionality, but now kind of next step is to do closed loop control with some of these robots, to do some of these automated manipulation tasks. So that's kind of where we're going with that. Okay. But yes, good eyes there. Okay.
Well, it seems for the moment, yeah, we have another comment. Thank you very much. Very inspiring talk. I would like to ask a question about vision-based deformation measurement. What is the resolution of the deformation measurement? What is the advantages and limitation on the force measurements from Farah Sadak?
Okay, so you're limited by the resolution of your camera, and your tracking algorithm. So we can do plus or minus 1 pixel, right? And so 1 pixel is, with our objective that we had, I think is like 5 microns or so. So if you have 5 microns and you have a certain stiffness, which is, micronewton per micron, right? Then you can figure out what the resolution is. So if you have a higher resolution camera, you can get better. Your 1 pixel may be 1 micron displacement, right? So that can help you tune your resolution. The one issue there is, if you zoom in, higher magnification, your workspace is a lot smaller, right? So it's kind of a trade-off there as well. If you want to see the whole thing and what's going on, you need to have a little bit bigger workspace. Advantages of this are that I don't know of any wireless untethered microscale force sensor on the market. So the only ones there are force sensing probes, which you can get and you can mount to a micro manipulator. Those are very, very expensive and sensitive, and we have some when we break them, and it's $5,000 to replace it. So that can be a problem. So these are very low cost, relatively speaking, and you can tune them, and you don't have any extra overhead for like electronics or signal conditioning. Some of those things are capacitive-based sensors. You need a lot of signal conditioning to get those and circuitry there. So this is a computer vision tracking system. Most biological labs, they have microscopes, they have cameras, and this will just be like a software package for them. And our coil system, we can actually design it to put it inside the microscope right around their system. So it should hopefully be easy to adapt.
Nice. Well, apparently questions are over. Thank you very much. I want to make a quick announcement before finishing this session. So the next webinar will be given by Professor Cedric Levy from Femtoeste Institute. It will be the 13th of March, Tuesday, at 1 p.m. UTC. It's about tethered microrobotics for complex tasks with submicrometer precision, from assembling of hybrid nanophotonic circuits to characterizing single plant fiber. So it would be our pleasure to have you with this talk. So again, Dave, thank you very much. Thanks all of you for being with us today. Don't hesitate to check the TC website that is given at the end of this slide to be aware of the new seminars. And yeah, I hope you enjoyed the talk. I did personally. So thank you very much, David. It was really interesting.
Yeah. Thanks, everyone. I appreciate it.
Nice.
Bye.
Well, see you. Have a nice day or a nice evening, depending on where you are.
Right.
Bye.
Thank you. Bye.